And now for an overview of the MIRI Imager. So the MIRI Imager has 9 filters from 5.6 to 25.5 microns, and they're designed to cover the full wavelength range without significant gaps in the wavelength coverage. So you can see that in the latest PCE plot from JWST here. I will say that all of the images and plots that I am presenting today are all on JWST. I think almost all of them are, maybe 1 or 2 aren't. So if you want to read anything in more depth, all of these are in JWST, and I provided the links for those at the end of the talk. We have a field of view of about 113 by 74 arc seconds. So this is the main imager field of view. That's the field of view. But we also have this bonus LEO field of view from the coronagraph. Because there's no additional optics in there, it does provide valid calibrated level 3 data. The other 4 QPM field of views do not have valid data because they have some other calibration that done. But you will get this bonus imager data from your observations. Now, MIRI has a very good sensitivity. We can observe very faint sources and very bright sources. So I've put on here the sensitivity plot, which represents the minimum detectable signal for all of the instrument modes. So here the imager is represented by the black circle, so you can see the very faint sources. And also I've included on here the bright source limits for all 9 filters. And so this is the brightness limit for the largest subarray, meaning the full array, full field of view. But if you want to observe even brighter targets, you can, because MIRI imaging does support a set of subarrays. We have 4 subarrays: bright sky, sub 256, 128, and 64. So we recommend using these only when it's required by the source brightness, meaning it would saturate the full array. And you should always rely on the ETC for the most up-to-date numbers when you're planning your proposals and plugging everything in. Always look for the ETC for the most detailed estimates. That's updated regularly, and it has had a recent update and ready for you to use. Next up, we're going to talk about the imager performance from what we observed during commissioning. So we had a PSF characterization commissioning activity. And here we observed a sample of standard stars. We have BD60, J17430, and a PN. And we created these MIRI PSF stamps. And this presented here on the images here. They're flat fielded level 2 data. And you can see in the wavelengths less than 10 microns, this cruciform pattern that is expected. And that's caused by internal scattering within the MIRI detectors. And you can also see the snowflake patterns at the greater wavelengths, the longer wavelengths. But we measured the measured Four-Wolf half maximums and then circle energies were all within a few % of the predictions that we had from WebPSF for all filters and in all field positions. So we have very good performance there. And the photometric stability is also very good. So we had repeat measurements about 12 days apart. They were all within 5%. So MIRI is performing very well in that regard. Now for some updates on the recommendation we have for observing strategies. The first one I'm going to talk about is mainly about dithers and how we use those to mitigate cosmic ray showers. So if you're not familiar, MIRI has these cosmic ray showers, which are basically just a pain. You see them as jumps in the data, and they take time to decay. So sometimes they'll be very small, sometimes they're streaky, sometimes they're fuzzy. I have some examples here of where you can see the primary hit, and then these small bright secondaries, and then this low-level glow that's affected in the background. And the pipeline does try to get rid of these. So we have the baseline jump algorithm. It will detect the primary hit. It will detect these brighter secondaries, but it's not going to eliminate this lower level glow that can sometimes result in a latent artifact. And there are also some types of showers that have no primary hit and they're not currently flagged by the pipeline. And so because of these, we want to recommend everyone to use dithers with large offsets to mitigate the cosmic ray showers. So what specifically do I mean by that? So for MIRI and APT, there are 6 or 7 dither pattern options offered. So that's going to be ranging in how large the offset is and what the pattern is. So this image here shows the number of overlapping frames. And we want the largest dither offset as possible to make sure that you can get rid of the cosmic rays, the bad pixels that are affected by the cosmic rays as they're decaying. And so the pattern that we're recommending now is the cycling large. So you're getting the large dither offsets, but still keeping a good field of view available for you here. You don't want to get rid of that, obviously. And we're recommending this for most cases. So we're recommending it for point sources, small and large extended sources, and mosaics. And we do recommend a minimum of 4 points to provide enough redundancy. And this is just the general recommendation. So again, a reminder to go into JDocs. There's a nice table there with all the dither patterns, the pros and cons of each one for your particular source. But this is one that we're recommending right now as the default. Moving on to more updates on recommendations for observing strategies. The next is that we are highly recommending the backgrounds be taken, and they're always recommended at longer wavelengths where the telescope thermal emission dominates, and the background subtraction is going to help mitigate other detector residual effects as well. So there's 2 types of backgrounds that you can have. So for point sources and sources that are smaller than the dither spacing that you choose, you can generate your own background using the science exposures. So the pipeline won't automatically perform this operation for you, but it will generate, but you can generate a science background exposure yourself to use. And this is an example of this over here, this image, ERO galaxy cluster image. So on the left, you have the dither combined images without background correction. On the right, you do have it with background correction. And on the right is also flat field corrected as well. So it's a combination of those two. But this background that they used was generated with the science data. And if you have a source that covers a large fraction of the field of view, it's advised that you do obtain a background, separate background data in every spectral configuration used by the science data. And in this case, APT will link these observations together, and the pipeline will do this background subtraction for you. And the background target we recommend should be observed in a similar way to the science data. So you should have dithering and at minimum use the same exposure time as the science data that you have. So those are the 2 main new recommendations that we have for MIRI Imager. In summary, performing very well, and even if not beyond expectations, and we're continually improving our calibrations and providing updates to you. We are ready for the Cycle 2 call for proposals and all these new discoveries that are to come. And of course, if you have any questions about the Imager, you can always submit a question to the help desk as needed, and it's there to answer. And here's the JDocs links at the end.